water is a polar molecule. When we add a new text, the delta, this symbol here, let me put it over. Can you guys see the funny little red dippy thing? I hope everyone can see that. That is lowercase delta. And that is used to represent partial charge. So water molecule has partial positive charge on the hydrogens because when the oxygen shares electrons, they share unequally. So the oxygen kind of tends to lose the electrons in the bond, and the oxygen tends to gain them. So the oxygen gets a partial negative charge. And when they do that, well, like before, I'll put a text box down here, opposite charges attract. So water is attracted to itself. Let's continue. Don't go to the mouse. Oops. How about we erase? Let me erase. Okay. So water has its own attractions. The oxygens are attracted to the hydrogens between molecules. And it's why water has a very low boiling point compared to metals. It absorbs a lot less heat energy. It has these very strong bonds. Another property of water, because it has these partial charges, is other things that have charges will dissolve into it. And water forms what we call a solution when something dissolves into it. So if, say, sodium chloride in water, then you have what we call a solution. And a solution is, we saw this from probably the beginning of class, is essentially a homogeneous mixture. It's a mixture whose particles are evenly distributed so that the relative concentrations of the components are the same throughout. So if I mix sodium chloride in water, and let's say I have a 5% solution, wherever I sample that solution, it will be 5%. Let me continue. Okay. Water solutions are specifically called aqueous, and that's that it's not a state of matter, but it's a fourth condition. Aside from being a solid, a liquid, and a gas, is something can be dissolved in water. This is showing a photograph of sodium chloride dissolved in water, and so the ions actually separate. So we can write it as sodium chloride aqueous can be written as sodium plus aqueous plus, let me expand that text box out, plus chloride minus aqueous. The ions are separate. So that's just a really important thing to know. If soluble, ionic compounds separate. Okay. So let's continue. I'll go down to the next slide. Solute and solvent. So let me erase what we had before. So the solid, or the sodium chloride, is called the solute, and the liquid is called the solvent. There's a more technical definition of that. Let's see here. In solutions of gases and liquids, then the gas would be called the solute, and the liquid would be called the solvent. So let me define those. The solute is the minor component of a mixture. expand the text box out. And the solvent is the major component. And usually by major, it means like 95% plus usually. Largely, it's usually overwhelmingly water and a very small amount of salt. Okay. So they come together and they make the solution. The solution is equal to the solute plus the solvent. So I believe I'm recording this, so we should have it for later. But if you want to take a screenshot, you can. Let me go back to mouse and click forward. So in other solutions, we call the minor component the solute and the major component the solvent. And the combination is the solution. Let me erase my text. Okay. So this is showing a salt crystal microscopically dissolving into water. And so the salt crystal is a combination of chloride ions as green and sodium ions as yellow. And as it dissolves, the ions leave the solid crystal and they get surrounded by the water. And so for the chloride, which has a negative charge, the partially positive hydrogen ends of the water molecule attract to it. For the sodium ion in yellow, which is positive, the negative oxygen end of the water attract to it. And the attraction of several water molecules to one ion are stronger than the attractions of the ions to themselves. And so usually these ionic compounds will spontaneously dissolve in water. Okay, let's continue. Okay. And so that's actually shown on this page. So the cations are surrounded by the negative oxygens, and the anions, the green, are surrounded by the positive hydrogen ends, right? Okay. You can have other solvents. So this is where we have pentane and hexane. And so that's another type of solvent. If it's not water, then the solvent needs to be named. So if I have a pentane solution, I have to say pentane dissolved in hexane. But if I just say sodium chloride solution, then that typically means water. If I don't specify the solvent, then we assume water. But pentane won't actually dissolve. These are actually what we call non-polar solvents in this example here. So there are other types of solutions besides water. And that brings us to precipitation reactions. So we can start this today before we run out of time, and then we can work on this in the next lecture on Wednesday. But we did talk about precipitation reactions already on paper. In a precipitation reaction, one product is insoluble in water. As that product forms, it emerges or precipitates from the solution as a solid. The solid is called a precipitate. So this is showing an example. If I have calcium nitrate solution and I react with sodium carbonate solution, meaning I mix two solutions together, then the ions can swap. And when they do that, if calcium ions find carbonate ions, those, where my cursor is, let me go back for a second. Oops. The calcium carbonate will form a solid. And that's a classic precipitation reaction as an example. So it's handy to be able to describe the solutions formed at the instant they're mixed. So in order to do that, we have to be able to do a double displacement reaction, typically, and describe that reaction accurately and describe the final mixture. And so there's a set of steps for these. Okay, and then writing the complete equation for the reaction. There's a process I'll go into more detail on Wednesday about. So this is showing the solution of calcium nitrate. So this is just a picture representation. So the water's in the background, and then the blue and red triangle things are the nitrates, and then the little yellow 2 pluses are the calciums. And so again, if it's a soluble ionic compound, these ions are separate, right? And, technically, because it's CaNO3,2, there would be twice as many of the nitrates floating around. And then we'll look at the other solution. If we mix into it sodium carbonate, so the sodium carbonate would be the little +1, I guess the orange balls, and the carbonate would be the black red triangles with the 2-. So now those are also separate. So I've mixed these two solutions together, and the calcium can then go find a carbonate. And when they do that, they start to form a solid. And so that's this process showing here. So I'm starting to form a little microcrystal of solid calcium carbonate. And when it does that, it blocks light. And then given enough time, I guess if you guys can look at the little Erlenmeyer on the bottom left corner, the solid particles are usually more dense than the solution. So they will, over time, fall to the bottom and make a sediment, which we didn't actually see in the lab because we were only mixing droplets.